Hello friends, welcome to my lecture on power series solution of second order homogeneous differential equations. We have seen that the solution of certain types of higher order differential equations, for example higher order differential equation with constant coefficients, can be expressed as a finite linear combination of known elementary functions, but such closed form solutions may not always be possible for linear differential equations of higher orders with variable coefficients. However, such differential equations do occur in many physical problems of engineering and science. One of the effective methods to obtain solutions of such equations is the use of power series. Often solutions through power series help us to solve non-linear equations also. Now, let us consider a second order homogeneous linear differential equation a naught x into y double dash plus a1 x into y dash plus a2 x into y equal to 0, and suppose that this equation has no solution that is expressible as a finite linear combination of known elementary functions. So, let us assume that however that it does have a solution that can be expressed in the form of an infinite series. Specifically, let us assume that it has a solution expressible in the form c naught plus c 1 into x minus x naught plus c 2 into x minus x naught whole square and so on, which in abbreviated form we can write as sigma k equal to 0 to infinity c k x minus x naught to the power k, where c naught, c 1, c 2 and so on are constant. An expression of the form 2 is called a power series solution of the differential equation 1. So, let us see now the question arises under what conditions this assumption of ours that is that the solution of the given equation 1 is expressible in the form of an infinite series, under what conditions this solution is valid. So, to answer this question, let us write the equation 1 in the normalized form by dividing the coefficient of y double dash throughout the equation, and then we get y double dash plus p1 x into y dash plus p2 x into y equal to 0, where p1 x is equal to a1 x over a naught x and p2 x equal to a2 x over a naught x. Now, a function f is said to be analytic at a point x naught if its Taylor series about the point x equal to x naught exists and converges to f in some interval containing the point x naught. So, here let us look at the normalized form. This is the normalized form of the equation 1. So, p1 x is a1 x over a naught x and p2 x is a2 x over a naught x. A point x naught is called an ordinary point of the differential equation 1 if both the functions p1 x and p2 x which occur in the normalized form are analytic at x naught. That means the functions p1 x and p2 x, the Taylor series of the functions p1 x and p2 x about the point x equal to x naught exists and converges in some open interval containing the point x equal to x naught. Now, let us consider y double dash plus x y dash plus x square plus 2 y equal to 0. So, here we can see that p1 x is x and p2 x is equal to x square plus 2. So, p1 x is a polynomial and p2 x is a polynomial. Both polynomials are analytic functions. We can write the Taylor series of p1 x and p2 x about any point x equal to x naught, and it will be convergent for all values of x equal to x for all x. So, these are analytic functions for all real values of x, and therefore, every point x of the real line is an ordinary point of the differential equation y double dash plus x y dash plus x square plus 2 y equal to 0. Now, here in this case y double dash plus x over x minus 1 y dash plus 1 over x into x minus 1 y equal to 0, we see that p1 x is x over x minus 1, p2 x is 1 over x into x minus 1. Now, p1 x is not analytic at x equal to x equal to 1, and p2 x is not analytic at x equal to 0 and at x equal to 1. So, we can write the Taylor series of the function p1x about any point other than x equal to 1, and therefore, this is every point x other than x equal to 1 is an ordinary point of p1x, and in the case of p2x every point other than x equal to 0 and x equal to 1 is an ordinary this function p2x is analytic about any x other than x equal to 0 and x equal to 1. So, the equation has ordinary point other than x equal to 0 and x equal to 1. So, the given differential equation for the given differential equation all real numbers except x equal to 0 and x equal to 1 are ordinary points. Okay, now let us state a theorem which will be used to find the power series solution of a given differential equation. Let x naught be an ordinary point of the differential equation 1, then one has two non-trivial linearly independent power series solution of the form sigma n equal to 0 to infinity C n x minus x naught to the power n, and these power series converge in some interval mod of x minus x naught less than r, where r is positive about the point x equal to x naught. So, we will use this theorem to find the power series solution of a given second order homogeneous linear differential equation with variable coefficients. Now, what we do is, suppose we are given a differential equation say by double dash plus p1x into by dash plus p2x into y equal to 0, then what we will do, we will assume the solution to be by equal to sigma, and x equal to x naught is an ordinary point of this differential equation, then we will assume the solution to be by equal to sigma n equal to 0 to infinity C n x minus x naught raised to the power n, and let us say that this series converges in the region mod of x minus x naught less than r, that is, it has a radius of convergence r. So, then we will find y dash sigma n equal to 1 to infinity n times C n x minus x naught raised to the power n minus 1, and this series also has the same radius of convergence. We will also find by double dash because we need the value of by double dash. So, sigma n equal to 2 to infinity n into n minus 1 C n x minus x naught raised to the power n minus 2 n mod of x minus x naught less than r. Now, we shall then substitute the values of y dash by double dash in the given differential equation, and then what we will have, sigma n equal to 2 to infinity n into n minus 1 C n x minus x naught raised to the power n minus 2 plus sigma n equal to 1 to infinity n into C n x minus x naught raised to the power n minus 1, and this thing is multiplied by p1x, okay, and then we have p2x into by. So, by is sigma n equal to 0 to infinity C n x minus x naught raised to the power n, okay, and this is equal to 0. So, this is valid for mod of x minus x naught less than r. Okay. Then we will have collect the coefficients of various powers of x minus x naught, okay, and we will have say k naught plus k1 x minus x naught plus k2 x minus x naught whole square and so on equal to 0. Okay. Now, then what will happen, these k naught, k1, k2 will depend on the coefficient Cns of the given of the power series, Okay. So, now by the identity principle, the coefficients of various powers of x minus x naught will be 0. So, k naught equal to 0, k 1 equal to 0, k 2 equal to 0 and so on. Okay. And once we have the values of k naught, k 1, k 2, once we put them 0, we will get a relation between the coefficients C n is obtained. From where we will be able to find the values of the coefficients C1, C2, C3 and so on, C0, C1, C2, C3 and so on, and then suppose by 1 is one solution and by 2 is another solution, then the general solution will be by equal to C1 by 1 plus or you can say A1 by 1 plus A2 by 2. So, we will get two power series solution, and the two independent solutions by 1 by 2 we will have by establishing the relation between the coefficients C n. Two power series solution will be obtained, and A1 A2 are two arbitrary constants. So, by equal to A1 by 1 plus A2 by 2 will then give the general solution of the given differential equation. Now, we shall be solving polynomial the power series solution we shall find for homogeneous linear differential equation with variable coefficients. So, P1 x and P2 x will be taken as polynomial coefficients here. So, what we do is let us consider the case of the differential equation by double dash plus x by dash plus x square plus 2 by equal to 0. So, what we see here is that P1 x is equal to x and P2 x is equal to x square plus 2. So, both P1 x is a polynomial in x and P2 x is a polynomial in x of degree 2. So, both are analytic functions. Their Taylor series converges for all values of x, that is the radius of convergence is infinite. So, they are analytic functions. So, every point every x belonging to R is an ordinary point of the given differential equation. Let us find the solution of this differential equation about x equal to 0. Okay. So, let us find the power series solution about, we can find its power series solution about any x equal to x naught. Let us for convenience let us take x naught to be equal to 0. So, let us assume that by equal to sigma C n x minus 0 to the power n, x naught is equal to 0 here, that is we have sigma C n x to the power n equal to 0 to infinity. Let us assume this to be a solution, assume that this by equal to this to be a solution of the given differential equation. Okay. And let us say R be its radius of convergence. So, then the series converges for mod of x less than R, and R is of course infinity here. So, the series converges for all x belonging to R. So, what we have, so sigma by dash then is equal to sigma n equal to 1 to infinity n times C n x to the power n minus 1 by double dash equal to sigma n equal to 2 to infinity n into n minus 1 C n x to the power n minus 2. So, let us put it here. What do we get? Sigma n equal to 2 to infinity from the by putting the value by double dash n into n minus 1 C n x to the power n minus 2, then x into y dash. So, we multiply x to y dash and we get sigma n equal to 1 to infinity n C n x to the power n, and then we multiply x square first to y. When you multiply x square to y, we get sigma n equal to 0 to infinity C n x to the power n plus 2, and then we multiply 2 to this. So, sigma n equal to 0 to infinity 2 times C n into x to the power n equal to 0. Now, this equation holds for all real values of x. Okay. So, what we do, let us replace n minus 2 y equal to j. Okay. So, this will be give you j equal to 0 to infinity n plus 2 into n plus 1. So, n plus 1 and sorry j plus 1, j plus 1, j plus 2, c j plus 2 x to the power j, and here we put n minus 1 equal to k. So, we put k equal to n minus 1. So, k is equal to 0 to infinity and k plus 1 and then c k plus 1 x to the power k plus 1. Okay. And this is sigma n equal to 0 to infinity C n x to the power n plus 2 plus 2 times sigma n equal to 0 to infinity C n x to the power n equal to 0. Let us put it like that, and then let us collect the coefficient of x to the power n. Okay. So, summation n is equal to 0 to infinity x to the power n is multiplied by n plus 1 into n plus 2 into C n plus 2. Then here from here n plus 1 C n plus 1. Okay. Okay, this is, oh wait, we are not writing, we are writing the coefficient of x to the power n. So, not this. So, this will be plus 2 times C n. Okay. Sigma n equal to 0 to infinity x to the power n multiplied to n plus 1 n plus 2 C n plus 2 plus 2 C n, and then we have sigma n equal to 0 to infinity C n plus 1 C n plus 1 x to the power n plus 1 plus sigma n equal to 0 to infinity C n x to the power n plus 2 equal to 0. Now, let us notice that this series this identity holds for all values of x. So, the coefficients of various powers of x will be equal to 0. Here when x is equal to, when we put n equal to 0, x to the power 0 we get. Okay. And here when we put n equal to 0, the least power of x that we get is x, and here the least power of x is 2. Okay. So, first let us put n equal to 0, so that we get the coefficient of x to the power 0, okay, which we put as 0. So, when we put n equal to 0, putting the coefficient of x to the power 0 to 0, we get, okay. So, let us put n equal to 0. So, 1 into 2, okay, 1 into 2 C2 plus 2 C naught is equal to 0, and what we get, C2 equal to minus C naught. So, we get the value of C2. Now, x to the power 0 term is not here, here also it is not there. Now, let us put the coefficient of x equal to 0. We get, okay. So, we put n equal to 1 here to get the coefficient of x. So, 2 into 3, and then we get n equal to 1 we are writing. So, C3, and then we get 2 times C1, okay. This, or here we will get the coefficient of x by taking n equal to 0. So, we get 1, and then n equal to 0 means C1. This is equal to 0, x term is not here. So, we get 2 into 3 C3 equal to minus 3 C1. So, C3 equal to minus 3 C1 divided by 2 into 3. So, that means minus C1 by 2. Now, we go to the next higher power of x, that is x square. that is x to the power 2 we get. So taking n equal to 2 now what we get. So all terms now will give the contribution when n takes values greater than or equal to 2. So when n is greater than or equal to 2, let us see what we get. Okay, when n is greater than or equal to 2, what will happen? Here the coefficient of x to the power n we are having. Okay, so x to the power n. So n plus 1, okay, n plus 2, then Cn plus 2, then we get 2 to the 2 Cn, this coefficient of x to the power n. Here the coefficient of x to the power n will be replaced n by n minus 1. So we get n into Cn. Here the coefficient of x to the power n we will get by replacing n by n minus 2. So Cn minus 2. So this is equal to 0 when n is greater than or equal to 2. Okay, so what do we get? Cn plus 2. Okay, so Cn plus 2 is equal to, let us write n plus 1 n plus 2. Okay, so n minus n plus 2 Cn divided by n plus 1 n plus 2 and then minus Cn minus 2 divided by n plus 1 n plus 2. So this n plus 2 cancels and we get Cn plus 2 equal to minus Cn divided by n plus 1 and minus Cn minus 2 divided by n plus 1 n plus 2, and n is greater than or equal to 2. So take n equal to 2 now. When you take n equal to 2, you get the value of C4. C4 will be coming out to be minus C2 divided by 3 when we put n equal to 2, and then minus C0 divided by n equal to 2. So we are getting 3 into 5. Now we have the value of C2 with us. C2 is equal to minus C0. So we get C0 over 3 minus C0 over 3 into 5. So this we can find, and this is equal to 15. So 5 C0 minus C0. So we get 4 C0. Okay. So this is how we get the value of C4. We can find then C5, C6 and so on from this relation, which is recurrence relation. Okay. We know the value of so what will happen here, you will have two arbitrary constants, C0 and C1. C2 depends on C0, C3 depends on C1. Okay. So C2, C4, C6 they will come in terms of C0, while C3, C5, C7 they will come in terms of C1. Okay. And then when we write the power series solution by equal to sigma n equal to 0 to infinity Cn x to the power n, we collect the coefficients of C0, that will give us one solution, and we collect the coefficients of C1, that gives us the other solution. Okay. And we will have the following situation. Okay. So we will have by equal to C1 by 1 plus C2 by 2, and the coefficient of C1 will come out to be 1 minus x square plus x4 by 4. Now one solution, one part here is the coefficient of C1 is 1 minus x square plus x4 by 4, the other part is x minus x cube by 2 plus 3x to the power 5. Here the powers of x are odd. Okay. Powers of x are odd means that we have the coefficients, these are the coefficients of C1, these are the coefficients of C1, and here this is the coefficient of C0 actually, this is C0 by 1 plus C1 by 2. Okay. So that we have written as C1 by 1 plus C2 by 2, but we will have y equal to C0 by 1 plus C1 by 2. Okay. The coefficient of C0 will be by 1x, 1 minus x square plus x4 by 4, and the coefficient of C1 will be 1 x minus x cube by 2 plus 3x to the power 5 by 40 and so on. And so you can see that this solution by 1x is a power series in x, and by 2x is also a power series in x, and they are not known functions. Okay, they do not represent known functions. So the solution of this differential equation is not in the closed, cannot be obtained in the closed form. It is given by power series which do not represent known elementary functions. The general solution will be by equal to C naught by 1 plus C 1 by 2. The coefficient of C naught is by 1, that is 1 minus x square plus x to the power 4 by 4, and the coefficient of C 2 is by 2x, which is x minus x cube by 2 plus 3 times x to the power 5 by 40 and so on, and the functions by 1x and by 2x do not represent known elementary functions, and therefore we can say that the power series solution of the given differential equation cannot be obtained in the form of as a finite linear combination of known elementary functions. It is given by power series which does not represent known elementary functions. With that I will come to the end of this lecture. Thank you very much for your attention.